Alright, so hopefully this is gonna be the first live stream version of our tutorials in this semester. I hope that all of these setups that I have here works as planned. I'm just trying to access the live chat here, so it should be popped up here. All right, here's the live chat panel, so you can basically ask your questions here in the live chat that we have. Ask your questions here. All right, so let's go to the code that we have, and yep, let's see what we're gonna do for this tutorial session. So basically in this session we are trying to implement a Python version of the binary search trees. Now let's first see what binary search trees are. In order to understand the binary search tree, well, we first need to understand binary tree. As we have the description here, and I will show you a picture that demonstrates the binary search trees afterwards. A binary tree, which is different from a binary search tree, of course. A binary tree is a hierarchical acyclic graph, and each node in that graph that doesn't have a circle may have up to two child nodes. Up to two child nodes. It can have no child, where in that case that node is just a leaf. It can have one child, or it can have two children. All right, so these two child nodes are called left and right node. So basically we have a parent node and we can have up to two child nodes. Each one of them are called left and right node. And these nodes usually contain some value and hold some information. And most of the time we hope that information is something of a comparable type, orderable type, that we can compare it with other nodes. So a node is holding, let's say, an integer, and the other node is holding another integer. We hope the two to be comparable. And so a binary search tree, however, is a special type of binary trees that has a condition, and that condition is that all the nodes to the left of the node, so the child to the left of the node, and all of the nodes in that subtree, in the left subtree, must have values less than or equal to the parent node's value. And same goes for the right node, but in that case they must have values greater than or equal to the parent node's value. So basically binary search tree is a special type of binary tree, and in that sense the two children, the left child must have a value lower than the parent, and the right child must have a value greater than the parent. So let's see an example here, hopefully. Okay. Right, I hope you see this example here. So this is basically a binary search tree example that we have here. So if you look at this node, 8 is the root of this binary search tree, and it's of course a binary tree because each node has a maximum number of 2 children. So this one is root 8 here, and it has a left child with value 3 and a right child with value 10. As you can see, the right child holds the value greater than 8 and the left child holds a value less than 8. That's what we want from a binary search tree. Again, if you look at the subtree that has this node 3 here as its parent, as its root, again the left child has a value less than 3 and the right child has a value greater than 3. But the point is, the right child of the 3 node here, it's a right child of this 3, but itself, the whole subtree here, is a left child of 8. So yes, anything to the right of a node must have a value greater than that node, that parent node, but this one itself is a left child of 8 by this proxy here, by this 3. So we can have 6 here, we can have 7, but we can't have 9. 9 is still greater than 3, but is not smaller than 8. So we can't have 9 here. So basically, everything to the left, everything in the left subtree of a node must have a value smaller than that node, and anything in the right of the node must have a value larger than that node. I hope this clarifies what we have and the definition of a binary search tree. So please, if you have any question, please have them asked on the discussion panel that we have. Now let's move to the code and try to run that. I am basically checking this discussion panel here, so if there's any question, please have them asked. If the concept of binary search tree is clear, we are now ready to go and implement that. But before, I think we have to increase the size of the probably, oops, that makes it a little big, but let's see how it looks. Yeah, it looks better. So yeah, let's go through it. So we're trying to, basically our task is to now write a binary search tree, a class named binary search BST, of course, that has the following method. So we know from the previous session that if we want to build a class, we have something like this here. So basically we can define a class like this, and we discussed that if that class is inheriting another class, we can put the parent class here, but in our case it's not inheriting any other class, it's not extending any other class, so we define it in this way. And as we discussed, for every class that we want to create, we need an init method basically, and if we don't put that there, it just treats it, the Python treats it as it is there already. We can't see it, but it's there, even if you don't explicitly define that. So let's say that this binary search tree takes a list of nodes called L as the nodes that we want to have in that binary search tree. So basically L is a list of nodes, and we have access to a binary search tree through its root. So basically, if we want to traverse through the binary search tree or have search for some value or insert some value or delete some value. We really need to start from somewhere and go through the binary search tree and perform our operation. And that operation needs and that traversal needs to start from somewhere. And what's the best place to start that? The root of the binary search tree, where we have access to all other nodes. And we have the hierarchy of the left child and right child having the lower value and the higher value. Okay, so let's say that we have a root node, and that root node has a left child, of course, but for now we initialize it as null, and that root node also has a right child, which we initialize as null as well. So let me check the discussion. All right, no questions so far. All right, and of course that root node itself, as we have for other nodes, holds some value. So that value, we expect the first element of the list to represent the value of the root. So imagine that if we want to have a binary search tree like that, we give it a list that looks like this: 8, 3, 10, 1, 6, 14, etc. All right, so let's have them. And the next step is to basically have the rest of the list. Well, let's say L, rest of the nodes, which are the nodes after the root. Okay. And basically we want to insert those nodes into the binary search tree that we have. So for every node in the rest of the nodes other than the root, of course, what we want to do is to just insert that node to the tree. But so far we don't have that insert method. All right, so basically we need to implement an insert method for the binary search tree that takes as argument a node and insert that node to its right place. So I hope the sound is clear, because someone is asking for the sound. Is the audio okay? Please respond. I really need to know that. Is the audio okay? Can anyone hear me? Okay, fine. Thanks for the feedback. All right, so basically the init method that you asked is the constructor of that class. So you can think of a class as a concept, an abstraction that represents real objects in the real world. So our program have some objects. Each object have some properties, have some methods, and those properties represent some values that are important to us. Those methods, like the insert that we're going to implement, represent some functionality that is important to us. And each object is a set of properties and methods. So you can think of an object like this. And the class is the abstraction, the generic type of an object. So we can have multiple binary search trees, but they are inherently binary search trees. So that's a generic abstraction definition of an object. And when we create an object, we have the real values. So you can think of the class as something that represents this structure and the functionality of this. You can think of an object that has these specific values and this specific ordering in that, as we code that to work in that way. All right, so let's see the description for the insert. So basically we don't want this, so we're trying to insert. So insertion has this description here. All right, so write a method insert that takes as its argument a node, a vertex, or whatever you want to call it, which adds a node to the binary search tree. So you can add the node wherever you want, but that node needs to that node cannot violate the concept of the binary search tree, that the left node has a value lower than the parent node and the right node or a right child has a value higher than that. All right, let's go and try to implement that. Def insert that takes as its argument a vertex, a node. So basically we have this self. I explained that. Let me see the discussion for a minute here, if you have any question. All right, so everything is fine. Let's go back to the code. So basically we are having a node and we try to insert that. But before that, I want to show you a demonstration of how insertion to a binary search tree works. So basically we have this binary search tree, we're trying to insert the nodes into it. So let's say 8 is the root. Let's insert that. By the way, let me put the link for that in the discussion here. So here's the link if you want to do that for yourself. So 8 is the root that we add as the first node, 3 is its left child as you see here, and 10 is its right child. So let's insert 10. As you see, this happens like this, nice and easy. The next node is 1. So basically we compare 1 to 8. It's smaller than 8, we have to go to the left subtree. We compare 1 to 3, that's the starting point I was talking about. Start from somewhere and insert. We compare 1 to 3 and we see that it's smaller than 3. Go to the left subtree. Boom, there is nothing in the left subtree. Insert that right there. So the next node is 6. We try to insert 6. So let me lower the animation speed a little. So basically we have 6 that compare with 8 is smaller than 8. Let's go to the left subtree. We compare with 3, it's larger than 3. Let's go to the right subtree, and as we have it here, let's now insert 14. So 14 compared with 8 here, greater than 8, go to the right subtree. Compare with 10, greater than 10, go to the right subtree. I guess you have the idea here. So let's go to the implementation. I also check the discussion, and the discussion is fine. All right, let's move to the implementation then. So as you saw in the graphical demonstration, let's say, of how we insert the a node to the binary search tree, we first compare the value of that node to the root. So basically self is pointing to the root. Self that has a value, that has a right child and has a left child. So self is pointing to the root. We compare the value of that node to the value of self. Alright, if that value is smaller than that, it means that we go to the left subtree, right? So basically left subtree. Now, if on the left subtree, let's look at this one again. If on the left subtree, remember when we start here, if on the left subtree, what 3 wasn't here at the beginning. Let me refresh this one. All right, let's insert 8. So basically we inserted 8 already in our code at the very beginning. Now when we want to insert 3, what happens is that it compares to the value is smaller, goes to the left subtree, and the left subtree it's null. So what we do now is that we know that we have to go to the left subtree, but if the left node of the root is null, it means that we have to put our new node there like this. We give it a list that has this value of v. So that node itself is gonna be the root of another subtree. So that has to have this left and right and value and all this concept that we have for the root itself. So it was the root, like the root of the whole tree, and when we insert 3 itself is going to be the root of another subtree. So basically we really need that initialization for that as well. So we set the left child of the root as the left as this new value that we have. Else it means that the left is not null. We have to go to the left subtree. Remember, we are in this if statement here. We have to go to the left subtree, but the left subtree is already occupied by a child. So what we do, that we insert the new vertex, the new node, to the left subtree, to the tree rooted with this left child. All right, we will see that the demonstration of that in a moment, but a quick explanation. So far we need to know, we already know that we have to go to the left subtree, and we already know that the left subtree in this else is occupied by a node called left. So we insert that to the left, the node that is represented by left. Now what happens is that, so basically here we can say else, or let's just say if has a value higher than that. So we can basically say right subtree. Let me check the discussion panel if there is any question. So far so good, no question. All right. So we have to go to the right subtree. Well, we do almost the same thing. If self.right node is not occupied. There's no one there, no one occupying there. Then, alright, just put it there. Create another, let's say, binary search tree that is rooted with the new node that we're trying to add, and put it there. But if it's occupied, then it's fine. Go to the right subtree that is occupied and insert the new node in the tree that is rooted, in the subtree that is rooted with this right node. Alright. So basically, we now have this insert method that we demonstrated in our in the web application. It's pretty straightforward. Now let's see what other operations does the question ask. So the next operation is probably search. Let me put the search here. Alright, so the search operation is described like this. Alright, so basically we were trying to write a search method that takes as its argument a value that we are trying to look up in the tree, which returns true if the integer value n that we are trying to look up appears anywhere in the tree. So basically, yeah, it returns true if the value is there, and if it's not, well, it has to return false then. Alright, let's def the search method. We're trying to look up for a value v or n. Let's keep it consistent and name everything v. Let me check the discussion panel. So far so good. Alright, so we have this search method here. If so, for the search, okay, so basically we have this search operation in our web application as well. That's good. Alright, so let's insert them again. You can see how it works quickly. And it was 1, 6, 14 then 1, come on, do it faster, 6, 14, and yeah, that's enough. Let's say that we are trying to look for 6. We are trying to look for 6. So compare with that, smaller than that, go to the left subtree. Greater than that, go to the right subtree. Boom! It's here, we found it. Alright? Found, as the web applications say. But let's say we're looking for 5, something that doesn't exist. Let's see what happens. Smaller than 8, go to the left subtree. Larger than 3, go to the right subtree. Smaller than 6, go to the left subtree. Oops, there is no left subtree here. So, element not found, which makes sense. We now have the demonstration of that. It makes sense. Let's go and try to implement that. Okay, so basically if you remember from what I just showed you, we compare the value to the root first. If it was there, then bingo, we found it, return true. But if it wasn't there in the root, some cases might happen. Either the left node is null, so if the left node is null, if you have that as false, I explain what that is in a moment, but let me just write the whole if else statement for a moment. if the left node is not null, then what happens? So, alright, if the left node is not null, then what happens is that val equals self dot left dot search for v. Again, let's also write for the right subtree as well. So basically, if self that's right equals null, right value equals false, else right value equals self dot right. Oops, what's this? Oops. All right. Go and try to find that self dot right dot search and v. Okay. So basically we return lval or rightval. All right. That's fine. Okay. So I cannot put the whole thing here, but that's the first statement of the search method. So we are basically trying to search for value v. So we start from the node root. This is the root here. If the value of the root equals the value that we're looking for, then it's already there. Return true. Otherwise, if the left subtree has a value, if the left subtree is not there, it's null, then we don't have that in the left subtree. But if the left subtree exists, we go and search in the left subtree. We can have a condition here that says if the left subtree is not null and the value is smaller than. So basically, let's say if v is smaller than self.value. So if the left subtree is null, then we can't have that in the right in the left subtree. Just mark it as false. But if the left subtree is not null and the value that we are trying to look up is smaller than the value in the node, in the parent node that we are working on, then go to the left subtree and search there. However, the reason that we have these two here as if statements is that in our version of the binary search tree, we can have values that are we can have duplicate values basically. So maybe it would be a better idea to not put this elif statement. So for binary search trees, we have two versions. Either there is no duplicate value, or it is allowed to have duplicate values. Since in our version we are allowed to have duplicate values, value may exist in the left subtree or in the right subtree. So basically, we don't here, if we found it in the left subtree, then okay, we found it. But if we didn't, we also check the right subtree as well, because we are allowed we allow duplication. So the same story goes for the right node here. If the right node is null, then there is no right subtree to go and search for. Otherwise, there is, go and search for. And then at the beginning, return whether you found it in the left or right, doesn't matter. We just want to know whether we were able to find it. Alright, good. No question. So basically what we have as the next method is max depth. Let's see what max depth is. This is a description of max depth. So a tree has a depth. You can think of the depth of a tree. So in this example, let's see here. So basically here the depth of the tree here is 1, 2, 3. It's literally the depth of tree in the common sense. So okay, let's go to our implementation, and there is no question so far. That's good. Maximum depth. The maximum depth of a binary search tree is defined as the number of nodes in the longest chain in the tree. Basically the depth of a tree. The maximum depth of a binary search tree. Alright, this is an example, but we are not using that example. So let's go and implement max depth. We can also name it like this. It's a better practice. Max depth. So basically, if the left subtree is null, then the lval for the left subtree is 0. We will see what that lval is in a moment, but basically we don't have we're looking for the longest chain that starts from root and ends with a leaf. So we're looking again, let me show you here. We're looking for a root that starts from we're looking for a path that starts from root that ends with a leaf. So 1, 2, 3. So basically if the left subtree, the entire part here is null, then we can't go from there, of course. We have to start our traverse from somewhere else. Else lval equals self.left.max depth. Here we are using recursion plus 1. So basically here we're saying that the longest chain that you can have in the left subtree is 1 plus the longest chain that you can have in what's remaining if we take the current node out. That makes sense. If I show you again here, so the longest chain that you can have in the left subtree starts from 8, go to 3, 6, and 4. We can say the longest chain starting in the left subtree of 8 is 1, that represents this level, plus the longest chain that you can have here. It's a recursive way of solving this. Alright? So basically we also need to do that for right node as well as what we did for search. If self.right equals null, then our path, our longest chain or longest path doesn't go through the right node. We have to just depend on the left node. But otherwise we can have almost the same thing that we had, well, the identical thing that we had for the left node. Same story goes for this one. And what we return is the max of lval and right val. Remember, a binary search tree is not necessarily a binary search tree is not necessarily a balanced tree. It can have a chain that goes all the way to right. Let me show you that. So let's just insert 1 and then insert 2 and then insert 3 and then insert 4, insert 5, insert 6, and let's just insert 0 for the concept of proof. So basically what we have here is this valid binary search tree that we have, and the left subtree, the longest chain that we can find is 1, but the right subtree, well, it has a long chain. So basically we need to account for that by using this maximum here. Hopefully there is no question so far. Okay, and what we need to do next, I think we are done with everything. So yeah, basically we have that. We have everything that we wanted to create. Okay, probably another method to represent the binary search tree when we try to print that. So basically, as I mentioned in the previous session, those methods of a class that starts with double underscore and ends with double underscore, and usually your IDE recognize that and highlight that in another color, in a special color different from what you have for your own defined method. Those methods are basically methods that belong inherently to that class. So this class inherently does have this init method, does have this str method, and they all come from object class. So basically we can put object here. Object is a class that every class you define basically and by default inherits that. And there are some methods in that that are available in the child class as well, and init is one of them that we use most of the time, and str is another one. Alright, if you don't put that there, it's okay, it's implicit. If you put that there, it's explicit, but it's always there unless you put something else, and that something else itself has object as its parent, so you can't skip that. This method is basically some kind of representation that we want to have for our binary search tree. I copied the representation so we don't have to go through it, but it's basically it. And let's see what happens if we try to, so in order to stay consistent with our own example, let's use the values that we have. Well, we don't necessarily need to stay consistent with the example. This example here has this. So we're trying to create a binary search tree with these values. 5 is basically the root, and these are the rest of the nodes. So the root that goes here, and left child and right child that we insert to the tree one by one. Let's try to run that and see what happens. So yeah, basically we have this output in the I'm not sure if that's visible. Let's see how we can make that visible. We need to add some margin here. Yes. All right. So basically it's a representation that it's not really human friendly, but it has the idea. We really can't print a binary search tree in a vel format, in a vel shape in the console. So let's go and see the online demonstration using the online tool that we have instead of this one. So basically what happens here is that upon calling this class, calling this object here, the init method is called. The first value, which was 5, I believe, yes, goes to the root, and the rest are inserted one by one. The insert method takes a node, compares that to the value with root. If it was less, we go to the left subtree, and we go further and further and further until we reach some place that is not occupied. And we do that recursively here. And that's the insertion. With search, we're trying to look up a node. We basically compare that to the value of root. If it was there, then we found it, done. Otherwise, since here we are we're allowing to have duplicate values, then we need to both traverse the left subtree and right subtree. But basically, we go to the left as long as we can until we reach some null node, or reach a node that has the value that we're looking for. So this is basically the base case of this recursive method. This is a recursive method. This one is calling that recursive method. All right. And we have this max depth that shows that calculates the maximum depth that we have for a tree. So the max depth, as I showed you, could be in the left subtree, or it could be in the right subtree. We need to compute both and then return the maximum of them. So let's see the discussion here. We have 3 minutes left. If you have any question, please have them asked in the discussion panel so that we can answer that. But I put the link that visualize the binary search tree in the discussion panel, in the chat panel. You can construct the tree for yourself with the example that we have, and you can also construct that in your code and compare how it works. So we have 2 minutes, and I assume that 2 minutes should be invested in questions. So if there is any question, please have them asked in the discussion. In the meantime, let's maybe go and why not? Let's create the tree that we have here. So let's have this one reset, and all right, 5, 3, 7, insert 5, insert 3, insert 7. Let me lower the animation, and then 8, 2, 4, insert 8. There is the place, insert 8. What was then? Next, 8, 2, 4, 7, 2. Here, it's less than 5, go to the left, less than 3, go to the left until we reach a place that is not occupied. 4, I believe, was the next one. Left, well, it's bigger than 3, let's go to right. 7. So basically we are having a duplicate value. So with 7, we can choose to go to left or right. In our code, I believe we choose to go left, but here it chose to go right. Doesn't matter. It doesn't violate the properties of the binary search trees. So 14, greater than 5, greater than 7, greater than 8 greater than everything goes to the rightmost place that we have in the tree. Insert 7, I guess, again, greater than 5. Wow, equal to 7. We chose to go right. We could have chosen to go left, doesn't matter. Here is the place to insert 7. Next one is 25. 9 and 1 are the next. Let's increase the animation a little bit. So 25, and then 9 to be insert. And discussion panel is empty. And the last element is 1. So basically, since we have duplication here, your code may behave differently, but if you remove the duplication, you must have the same result as we have here. So discussion panel is still fine here, and yeah, it's 12:21. I guess we can end this live stream. Thank you.